C5, placeholders for integration. Now, different disciplines have different approaches to handle this. Let me show you what I'm talking about first. If you're integrating from 0 to 1 of x dx, there's no ambiguity. You would say, if you're integrating, you would take the integral, you would say x squared over 2 is integrating x dx and evaluate from 0 to 1. And then you would put in 1 for x, get 1 squared, 1 over 2. And then you would put in 0 for x and subtract 0 over 2. And the answer is 1/2. No ambiguity. Everything's cool. If we go from 0 to x sub 1, there's also no ambiguity. We would have x squared over 2 from 0 to x1. We would put in here the x1 first. So let's say x1 squared over 2. And then minus 0 for the x, 0 over 2. And you would get x1 squared over 2. No problem. No ambiguity. But if we were to do this, 0 to x and x dx, now what's going on here? That looks a little weird because you're integrating over this variable and you're using the same variable as an integration limit. Like, what's going on there? So let's review for a second what is the idea of taking an integral. And I'll use this S for sum because in the old days they would do strips of area. Let me show you this basic idea. If you're integrating under a graph, the integral is equivalent to taking the area, if we're going to go from, say, A to B, like this, of some function f of x dx, and this is our y, which is our function f of x, which is, doing this sort of thing. Then we're interested in the area. This is S, the area. And, we would do strips, for example, when we introduce the concept of integration in calculus class. So we'll use that S for a sum of the strips. But this is what you would get from A to B. You would get this area. All right. Now, if we look over here, this is what physics professors like to do. They like to go from 0 to x of f of x dx and not worry about making this a different variable. So in other words, what they're saying is, we're going to go, in this case, from 0, and we're going to stop, that's the x-axis, we're going to stop at some arbitrary x here, and we want this area. That's what we're interested in. Now, let me show you how some disciplines, like atmospheric science, for example, and mathematics, will work with this. They don't like what I just showed you up there that physicists like to do. So in other words, they use an integration variable. All right. But I'm going to defend the physics approach in a second, but I want to give you both sides. All right, so we go here from 0 to x, and the integration variable, we would change it and say x prime. So now it's not confusing where there's x in both places. You have x prime, then you have x. So you integrate this, you would get x prime squared over 2, and from 0 to x is different variable, a different thing. So you would have here then x squared over 2 minus, and then a 0 over 2, and you would have x squared over 2. Okay, all looks good. Another technique to handle this problem is to work with the integration limit. So in this case, we keep the x dx there, but we go from 0 to x prime, like this. So we have this integral, which is going to be a function of x prime, like this. So you would do x squared over 2, no problem there, and then you go 0 to x prime, and this would be x prime squared over 2 minus 0 over 2, which should be x prime squared over 2. Everything looks good. And then what you would do is you say, well, look, that's x prime as an argument for a function, I function of x prime. Let's just change it. Let's just make it x. And if you make it x, then this becomes x squared over 2. Now, these are the clean ways of doing things. Mathematicians would prefer this, and your calculus teacher would probably prefer that. So here, I want to show you, though, what we do in physics, all right, the convention physics. So let me show you a problem in physics, and I'll do it 2 ways. I'll do it using one of these tricks first, which is clean, and I got this idea from a book on atmospheric science and meteorology, a nice book by Petty. And what Petty would do with an integral like this, let me first give you the integral without worrying about the physics, where it came from. We're basically looking at integrating here on the right-hand side from 0 to some time t of a t prime dt prime. Now, if we integrate that, we would get a t prime squared over 2. You evaluate from 0 to t, and you would get then 1/2 at squared, because at the lower limit you get 0. And this is the famous formula that the distance is equal to 1/2 times the acceleration times time squared. Like if you drop a ball, for example, near the surface of the Earth where the acceleration is constant, often they just say that's g and put down 9.8 meters per second. But my point is not to really do the physics here, but to show the mathematics, the integration, how it's handled. Now what I would like to do is show you how it's handled in a physics book. In a physics book, actually this thing here, in a physics book would come from this integral, from x equal x naught to x, same x, see in both places, equal from this time integral from time 0 to t, some general t. And this would be, here's a general formula, the initial velocity plus the acceleration times time dt. But don't worry about these parameters in here. I'm quoting the physics book here just to show you the idea that the physicist is throwing a t here, a t here, a t here, a t there, t everywhere, all right? And not worrying about these primes and things like that. So then what the physicists would do here, this is v naught, times t. You would have here v naught times t, and the second one would be 1/2, because you would have t squared over 2. You do an integral like that, and you would go from 0 to t, and the lower limit is 0, so you would simply have v naught t plus 1/2 at squared, and you get the famous formula. See that the distance, or x, is x naught, plus this. This is a famous formula. So that's what a physicist does, all right? Now I'm going to give you another example, and this one comes from Feynman's famous lectures at Caltech. So he's doing this integral with the k, spring constant, and we're not worrying about the physics, just the integral here. And we're going to go here from 0 to x. X is everywhere. So when we do this, we get k, x squared over 2, then 0 to x, and we get here k, x squared at the top limit minus 0 squared at the bottom limit, and we get 1/2 kx squared. That's potential energy for a spring, but that need not concern us here. It's just the integral I wanted to talk about, that the integration variable is the same as the limit, the upper limit here. And another example that's famous in physics is where you have mass with the integral from 0 to v, velocity of v dv. You would have m, v squared over 2, and you'd go from 0 to v, and you would have 1/2 mv squared at the upper limit minus 0. Or if you had, say, a v naught down here like this, you'd have minus 1/2 mv naught squared. This is a famous equation that a change in kinetic energy. My point is, though, it's not to worry about the physics, but the mathematics. V here, V there, V here, V everywhere, all right? And there's no problem. Now, in our course on normal gravity, we will actually encounter the potential for gravity as a function of z, height, And this is approximately the integral of g dz, where g is roughly constant, but it's not constant. So we will consider that as an approximation. And we go from 0 here to some z, like that. And that would be g integrate from 0 to z dz, which should be g, and it would integrate z, because there's a 1 there, that integrates to z. If you take the derivative of z, go backwards, you get 1, from 0 to z, and that's simply gz. Now, it's interesting that what we're doing in this course with normal gravity, this similar equation appears in atmospheric science book, the Petty book. So in the atmospheric science book, he writes, and I'm quoting his book now, this is approximately 0 to z. He uses dz prime. So he's using the integration variable way to clean this up. And then that's going to get you g z prime, 0 to z, and that's going to be then gz, the same thing. And in a math class, probably the mathematics teacher would prefer this way, just like the atmospheric science one. But you know, physicists do not prefer that. They prefer what I did here and what I did here. In fact, the physics community would find this prime actually confusing, like you're making it more complicated. You're starting to introduce more variables. We don't need that. So the physics folks would not like this. They would prefer this. And since I'm a physicist, I'm gonna use this. You can consider that it's understood that you could always do the integration variable or the integration limit idea, and in a sense cleaned it up a little bit. But here, I'm not going to do that. So we're not going to use placeholders. All right, we'll see you next class.